In section 5.2 we're going to be looking at the definite integral and an introduction to Riemann sums. And actually section 5.2 kind of runs into the fundamental theorem of calculus in 5.3 and the fundamental theorem of calculus part 2 in 5.4. So a lot of these sections will kind of start to meld together, and it's a little bit more difficult to distinguish where one topic begins and another ends. Before we can talk about the definite integral, we need to go ahead and review a little bit what we've already talked about in terms of finding area underneath curves. When we were working in section 5.1, we were looking at area underneath a curve, and we took the limit as n approaches infinity of the left endpoint approximation, which would be identical to the limit as n approaches infinity of the midpoint approximation, which is the same for the right hand approximation. Now as n approaches infinity, we're talking about an infinite number of rectangles. Now this value will all be the same, and so this will be some value of L, let's say like 10. So the area underneath the curve would be 10 units, 10 square units. Well, this only works if this value of L represents the area underneath the graph when the graph is above the x-axis. If the x-axis, or if the graph is below the x-axis, then this is not true area. So that's something that we need to keep in mind. So again, this only works is that the entire graph of f of x is above the x-axis. Now this process that we worked with assumed that we had all rectangles of equal width. So we couldn't have one rectangle of a width of a half and the other rectangle of a width of 4. So we assumed all rectangles here would have the same width. In section 5.2 we relax some of these requirements and we start working with Riemann sums. Actually, the left, right, and midpoint approximations that we were doing before are a special case of Riemann sums. Riemann sums are a more general approximation to the area. And Riemann sums help us define what a definite integral will look like. So if you've ever heard of a definite integral, this is how they work because of Riemann sums. And this is Riemann himself that developed the concept of Riemann sums. Now we don't use Riemann sums a lot computationally, we use it to prove other theorems mostly. But we'll run through a couple of examples of how and why it works in order to kind of expand it into the idea of a definite integral. A couple things change from left, right, and midpoint intervals in section 5.1 to Riemann sums. First of all, for a Riemann sum, rectangles don't have to be of the same width. And also, instead of having to plug in a left, a mid, or a right endpoint to find the height of our function, we can plug in any value we want in the subinterval or of the width of the rectangle. So I have a lot of fewer restrictions to work with the Riemann sum. Now one of the important definitions of a Riemann sum is to define a partition. A partition is basically the width of a rectangle. Now when we talk about the width of a rectangle, because it's a Riemann sum, they don't have to be of the same width. So down here we see that this is a particular partition that we could work with. This would be a partition of length x1 minus x0. Here we'd have another partition from x1 to x2. The width here would be x2 minus x1. And then here's another partition, etc. Now what we like to talk about is the norm of a partition. Now the norm of all the partitions is basically the widest rectangle. So in this particular case, the widest rectangle definitely looks to be x2 minus x1, so I would call this the norm of the partitions. Now what we like to do then is take this idea of the norm of the partitions, and we like to take that width, and we like this width to go towards 0. So we'll take the limit and we'll take the norm of the partition, we'll go towards 0. Now as these rectangles get more and more narrow, I get more and more rectangles in the entire interval, and of course I get a better approximation of the area underneath the curve. And of course this works as area if this is above the x-axis. If part of this graph would be below the x-axis, then I kind of have to change my interpretation of the results. This is the formal definition of a Riemann sum. If you would ever need this formula, it would be provided for you on tests and quizzes. Let's go ahead and look at the definition. This says I want to sum, and of course we're going to be summing rectangles, and we're going to be summing the area of rectangles. So to interpret this, we're looking at the base, which is the delta x sub I, and this means the width of the ith interval, because again they don't have to be the same. And then f of c sub I means the height. If I plug c sub I in as my x value, f of c sub I is my height. So the way that interprets over here then for this particular rectangle that we have, this width right here from x sub I to the previous x sub I minus 1 is my delta x sub I. And then the height, I can choose any value in this subinterval to plug in to find my height. And they plugged in this c sub I value. So it makes sense. The formula looks a little bit complicated, but it makes sense based on base times height for each of these rectangles. And this is assuming a formula for n rectangles. So let's go ahead and look at an example where we're actually calculating out a Riemann sum. So this problem says to calculate the Riemann sum for the function f of x equals x squared plus x, and it gives us a value of partition points, and it gives you these values that they want you to plug in to find the height of the rectangles. So these are x values that I'll plug into the function to find my rectangles. The best thing to do probably to start out with is a quick curve sketch. The graph of f of x equals x squared plus x is a parabola opening up with its vertex at the origin. And we're interested in this particular graph from 2 to 5. So let's go ahead and focus in on those points from 2 to 5. And of course, if we go from 2 to 5, there's also a 3 and a 4 in between to split this up as integers. Now these values of our partition tells us that we want a partition at 2, 3, 4.5, and 5 to draw my rectangles. So the first partition is at 2. Our next one is at 3. So there's our first rectangle. The next partition is at 4.5, which is right here. Whoops, make that a little bit more straight. And then my last partition is at 5. So here's my last partition. So I have 3 rectangles here. This last one is a very narrow rectangle, but I still have a rectangle there nonetheless. Now these next points say, well, what is the height of each one of these rectangles? Well, I have a lot of different points right here where I could choose for the height of the rectangle. This value up here at 2 says let 2 be the height of that first rectangle. So if I plug 2 into this function, I come back up here for my y value, and that's the height of the first rectangle. So I want to find the area of this rectangle. All of this up here in this region then would be an underestimate. So this is a circumscribed rectangle. The next one says plug in 3.5 to find the height of the next rectangle. So if I plug in 3.5, this is the height of my next rectangle. Okay, so I want to find the total height of this rectangle. For my last one, it says to plug in 5 to find the height of this last rectangle. And if I plug 5 in, I get this value back out, and I want to find the area of this fifth rectangle. Of course, there's error involved in each of these rectangles. This is an underestimate, this is an over on this piece, but an under over here, and this is just strictly an overestimate. So what we want to do next is to find the Riemann sum, so let's go ahead and look at the Riemann sum formula. This Riemann sum formula is pulled directly from our formula that we had up above. This case I'm looking at 3 rectangles. I know I have 3 rectangles because I have 3 points I'm plugging in, and also I have 4 sections that I'm splitting up here, so I have 1, 2, 3 points in between. So I have C1 for my first rectangle, C2, and C3 for my last one. So I need to plug these points in to my function. In plugging in then, I get f of 2, because my first partition point is 2, times the width of the first rectangle, which is 3 minus 2, plus f of 3.5, because they said to plug 3.5 in to find the height of the second rectangle, times the width of the second rectangle, which is 4.5 minus 3, plus f of 5 times the width of my third rectangle, which is 5 minus 4.5. So again, plugging in f of 2, I get 2 squared plus 2. 3 minus 2 is 1. 3.5 would be 3.5 squared plus 3.5 times 1.5. And again, these f of values I'm plugging right up here into my original function. Plus f of 5 would be 5 squared plus 5 times 5 minus 4.5 is 0.5. Okay, so running through and calculating this out, I get 44.625 units squared. Now what this is this is my approximation. This is my Riemann sum approximation for the true area underneath the curve from 2 to 5. And the curve that we're looking at in this particular case is x squared plus x. And we'll see here in just a minute that this actual value of 44.625 as our estimate is actually pretty low from the actual area underneath that curve. Now let's go ahead and look at how the idea of Riemann sums associates to the idea of the definite integral. This is the definition that your textbook gives us about what a definite integral is. This notation, the integral from a to b of f of x dx, will kind of pull apart here in a moment. But in general, what ends up happening is this norm, this partition, this largest value, we want the width of the rectangles to go towards 0. That's what this notation is meaning. So we want the width of the rectangles to go towards 0. That means we want smaller and smaller rectangles. The smaller the rectangle, the less error that we have in our estimation, whether it be an over or an underestimate. And then that ends up being this Riemann sum. So this is basically summing an infinite number of rectangles with an infinitely small width and finding the area of those, and that turns out to be the same as a definite integral. If this limit exists, because it won't always exist, we say that this function f of x is integratable over a to b. Now another theorem that kind of goes along with this talks about when a function is integratable. So this theorem says if we have a function that's continuous on the entire interval ab, then the function is integratable over ab. Now in Calc 2 you're going to run into some exceptions to this rule, but along with the exceptions we'll learn to deal with some tools to help actually integrate those types of functions. So let's go ahead and look at the integral from a to b of f of x dx. And like I said, let's go ahead and pull it apart and kind of look at all the different pieces of this. First of all, f of x is called the integrand, and we've talked about this one before. D of x is called the differential. This integral sign basically means to sum. It's like our sigma sign. Now, so what we're summing, or what we're adding up here, is the height. The integrand gives us the height of each of the small rectangles, and the differential gives us the base, or the width. And so this means to sum up all the rectangles, base times height, from A to B. And of course we want very, very small rectangles in terms of their width, and so that way I have very, very little error. And when I sum up these rectangles from A to B, then I should get the area underneath the curve as long as f of x is above the x-axis. B is my upper limit of integration, and A is my lower limit of integration. And like I said, these sections that we're working on will kind of start to blur because we're already getting into some things in section 5.3 when we talk about the fundamental theorem of calculus part 1. Now in this particular example we always have an x here, f of x and dx. Your functional value and your differential in Calc 1 need to match. When we get into Calc 3 they don't necessarily need to match. So in this case you can use any variable, not just x. So when we're looking at this particular example, I could have used f of y or f of t as well. So let's go ahead and look at an example using the techniques we learned in section 4.8 and using this idea or this concept of a definite integral. So let's go ahead and look at the integral from 2 to 5 of x squared plus x dx. And we actually just did this problem. So this is looking for the area underneath the curve, x squared plus x from 2 to 5, and so I'm looking for this area. So instead of writing out rectangles, what I'm going to do is actually apply this definition of the Riemann sum as the partition norm approaches 0. Well, we already know how to integrate x squared plus x. That's just x cubed over 3 plus x squared over 2. Now usually I'd put a plus c here for my constant of integration, but I don't have a constant of integration because I have a definite integral. So this is a definite integral because I have limits of integration. So what I do then is I evaluate this solution, this cap f of x, at my limits of integration. So this vertical bar means evaluate from x equal 2 to x equal 5. Now when I evaluate, I always plug in my upper minus my lower. Just like if I were to find the distance up here between 2 and 5, I take my right endpoint, my upper minus my left. So I'll do the same thing here, and I'll plug 5 in to my solution. So I'll have 5 cubed over 3 plus 5 squared over 2. That's my upper. Now I need to subtract out my lower. Now a common mistake here is to not put up your parentheses, and then the negative sign won't distribute through. Okay, so again, if I don't put up these parentheses, the negative sign only goes to the 2 cubed over 3. It does not go to the entire sum. So always your upper minus our lower. And again, this is kind of jumping ahead into section 5.3, but it's a good thing to know right now. So simplifying here, we end up with 125 over 3 plus 25 over 2 minus 8/3 minus a negative, or sorry, minus a positive is the same as a negative 4/2. So simplifying, I have 117 over 3. 125 minus 8 is 117 over 3. 25 halves minus 4 halves is plus 21 halves. Finding a common denominator of 6, I end up with 234 over 63, or sorry, 234 plus 63 over 6, which is 297 over 6, which reduces by a factor of 3 to 99 over 2. Now as a decimal approximation, this is 49.5 units squared. This is not an approximation, this is actual area. So before, we had an estimation of 44.625 in the problem we did just above the Riemann sums. Now because this entire region is above the x-axis, I can say that this is the actual area covered, and it's exactly 49.5 units squared. It's not an approximation. Well, speaking of whether it's above or below the x-axis, let's go ahead and look at graphical interpretations of the definite integral. Again, we like the best case scenario if our function is continuous and positive, and meaning it's positive means it's above the x-axis over an interval, then the definite integral f of x dx integrated from a to b is the area bound by the graph in the x-axis. So that's similar to the problem that we just did. In the problem we just did, we had f of x equals x squared. It was bounded below by the x-axis, above by my function from 2 to 5, and that was my area of interest. Now if that's not the case, things don't work out so well. We have to interpret it a little bit differently. If your function is not all positive, then the definite integral of f of x dx from a to b does not equal the true area like we would think. What ends up happening is we end up combining positive and negative area. So if we were to look at a graph, let's say, of a parabola opening up, part of this parabola is above the x-axis and part of the parabola is below. So if we were to, so for this particular graph, let's go ahead and say we're interested in finding the area from this value of a, let's go over a little further, to this value of b. So we have quite a bit of area here. This area up here would be positive area, so I'm going to shade that blue. This area over here would be positive area as well. Now this area beneath the curve would be negative area. So if I actually found the integral from whatever this point is to here, I'd get a negative number here. Up here, I would get a positive number. Over here, I'd get a positive number. And then I would add all these together, and when you add them together, you would see that this area down here would cancel out with some of the positive area up above. And so my true area is not really what I'd get here. My true area, what I'd actually be looking for, would be to find this number, find this value, and then this area in red, what I'd want to do is negate it to find out how much area is actually there. It's negative because it's telling me it's below the x-axis. So we have to be kind of careful about the interpretation of these. So knowing the general shape of the graphs is a really good idea, because then I can talk about whether it's really actual area or not. Let's go ahead and look at an example where we're finding the integral from, let's do a trig function here, from pi over 2 to 2 pi of sine of x dx. Okay. Well, first of all, I'm interested in knowing, if I find this, whether this is true area or it's going to be signed area. So first of all, we know the graph of the sine of x pretty well, so let's go ahead and sketch that up. So the sine curve looks something like this. It's going to peak at pi over 2, cross at pi, minimum at 3 pi over 2, and cross at 2 pi. And this limit of integration means I'm interested in the graph from pi over 2 to 2 pi. So here's pi over 2, and then here's 2 pi. So there's two regions here that I'm looking at. I have some that's positive above the x-axis and some is negative below the x-axis. So looking at this and understanding that the sine curve is symmetrical, it has as much area above as it does below, this red area is going to kind of overpower this blue area, and so my total area will end up being negative here. So this area below the graph is more than the area above the graph, so our total area will end up being negative. Now if I actually wanted to know how much area was covered from pi over 2 to pi, and not the signed area but the actual area from pi to 2 pi, I would have to change my limits of integration, and I'd have to kind of look at these in separate regions. Let's go ahead and find this signed area. The integral of sine of x, okay, the derivative of sine is cosine, therefore the integral of cosine is sine. The derivative of cosine is negative sine, therefore the integral of sine is negative cosine. So I get my integral here to be negative cosine of x, and I want to evaluate this from x equal pi over 2 to x equal 2 pi. So we go ahead and plug in our upper limit of integration minus our lower limit of integration. So cosine of 2 pi is 1. Minus a negative is the same as a positive. Cosine of pi over 2 is 0. And I get negative 1 here for this signed area. So this is not the actual area covered, this is the signed area. And as it turns out, if you were to find the area of each of these pieces for each of these quadrants, the area in this piece is 1, the area in this piece is 1, the area in this piece down here is negative 2. So what ends up happening, because of symmetry, each of these smaller pieces is negative 1. So I have negative 1 plus negative 1 plus 1 gives you my negative 1 value here. So this is signed area, it's not actual area. So it's a good idea to look at a curve sketch to know what you're working with, signed area or actual area. In order to work with integrals, we need to know some properties of definite integrals. The first property of definite integrals that we're going to look at has to do with reversing the limits of integration. Well, usually what we have is a type of an integral from a to b of f of x dx. Well, if we did the same function and we integrated it, but we switched our limits of integration, what ends up happening is you end up negating your solution. So if I flip my limits of integration, flip the order, it doesn't matter if they flip from small to large or large to small, you just end up negating your solution. So that's the first property of a definite integral. You can negate your solution by flipping the limits of integration. So if for some reason it would be easier to evaluate in another direction, you can flip your limits of integration. The next thing that we're going to look at for properties of integrals is to look at an integral whose limits of integration don't change. So for this one, instead of going from the limits of integration from a to b, this one goes from the limits of integration from a to a. Well, the integral of anything from a to a is going to be 0. It doesn't matter, because this is saying what's the area underneath the curve from a to a. And there's no area above a single point, so of course the area total would be 0. We could also look at the additivity for adjacent intervals. So what the additivity for adjacent intervals means is if we have an interval where a is the smallest value, b is a middle value, and c is our largest value, if I want to look at this interval from a to c of our integral of f of x dx, I can split it up into smaller pieces in order to find the overall solution. So pictorially that might look like I have a curve from a to c. And if I want to find this total area, what this is saying is I can actually split it up into two pieces. I can find the area of a to b first, and then I can find the area of b to c and add them together to get my total area. Now you might say, well, why would I want to do that? Well, in this instance, you wouldn't want to, because this is a nice little function. But there's other functions that might be piecewise functions that I can find the overall solution by splitting it up by the domain restrictions on the pieces for the piecewise function. I think to finish up, let's just go ahead and look at working a lot of problems. This first example, I would like to look at the integral from -2 to 3 of the constant 4 dx. So pictorially what this means is I'm interested in the x-axis from -2 to 3 of whatever this function looks like. In this particular case, the function is 4. This is y equal 4, f of x equal 4. So here's a graph of y equal 4. And of course these points intersect, and this is my total area of interest. Well, you don't even have to integrate to find this area. It's just a rectangle. The base here is 5, the height is 4, so my area here should be 20 units squared. But let's go ahead and look at this in terms of a definite integral as well. Now remember, when we're integrating from -2 to 3 of 4 dx, that's the same as 4 times x to the 0 dx. So I'm looking at integrating a constant. Well, when we integrate, remember we add 1, so 0 plus 1 is 1, divide by the sum. So I end up with 4x. No plus c here because I have a definite integral, so I'm evaluating this from -2 to 3. And I should be a little bit more specific here. This is x equal -2 to x equal 3. So we go ahead and plug in our upper minus our lower first. Now, an interesting thing about this constant that's out front is I can pull it out front, anything that's constant, nothing that's variable, and then evaluates what's remaining. So what's remaining is the x. So my upper is 3, and then I evaluate using my upper minus my lower. So I have 3 minus, that's my upper, minus my lower. My lower is -2. So I need to be careful here. I have 3 minus a -2, which leaves me with 4 times 5, which is 20 units squared. So that works slick. Now again, the integral of a constant is just the constant times whatever value the variable is. Now if you didn't like pulling this 4 out front, we could have done this a little bit different. I could have plugged in my upper, 4 times 3, minus my lower, 4 times a -2. And here I get 4 times 3 is 12, minus a negative is the same as a positive 8, so I get 20 units squared here as well. It's just a little bit easier if you can pull out any constants because your numbers get smaller that way. Okay, so for this next one, let's go ahead and combine some of our integration techniques. So let's look at the integral from 0 to 3 of 6y squared plus 7y plus 1 dy. We don't always have to use x's. Oh, and a quick note, this 20 units squared, this is true area because this entire graph is above the x-axis. Okay, so let's go ahead and integrate as we usually would. We'd add 1, divide by the sum, 6y cubed over 3 plus 7y squared over 2 plus the integral of a constant is just the constant times the variable, evaluated from y equals 0 to y equal 3. And of course we're going to simplify here. 3 goes into 6 twice, 2y cubed plus 7 halves y squared plus y, evaluated from y equals 0 to y equal 3. So we plug in our upper first. Our upper is 3, so I have 2 times 3 cubed plus 7 halves times 3 squared plus 3 minus our lower, which is going to be 2 times 0 cubed plus 7 halves times 0 squared plus 0. Now this entire lower piece goes to 0, but I should always check it. And then for my upper piece, it looks like I have 3 cubed is 27 times 2 is 54, plus 3 squared is 9, 9 times 7 is 63 over 2 plus 3. So this is 57 plus 63 halves. Finding a common denominator, I have 114 plus 63 all over 2. And of course, adding those together, I get 177 over 2. Now the question is this true area? Well, it could be signed area if I have some of this above the x-axis and some below, or it could be true area if this is entirely above the x-axis. So one way to figure this out would be to actually graph this in Maple. So let's go ahead and graph this in Maple and then get an idea of if this is true area or not. And then we'll also look at a definite integral in Maple as well. So if you need to, pause and open up Maple. Okay, so in Maple, if you want to, you can switch everything in terms of x, but we could just graph this in terms of y too. It doesn't end up mattering. I'm just going to put everything in terms of x to make it simple to work with. So our function, our original function that we were looking at, was 6 times x squared plus 7 times y, or x, sorry, 6 times x squared, have my num locks on, plus 7 times x plus 1 is my function, and I want to put a semicolon there, and again my num locks keeps coming on. So here's my function. Right click plots, 2D plot, and here's my graph. Now this is not very useful the way it's written. Now remember, I'm only interested in this graph from 0 to 3, so let's go ahead and change our domain here to match a little bit closer to that. So let's go 0 to 3. And it looks like I'm definitely above the x-axis between 0 and 3, and my horizontal scale is awful here, or my vertical scale is bad here too. Let's go 0. Looks like 100 would be plenty, and this looks much better. So I can see between 0 and 3 I'm entirely above the x-axis, so my estimate of 177 over 2 is true area in its units squared. Now if I wanted to check my answer, you can come up here to your expressions palette and choose your integral function. Now remember, on our expressions palette, this one is our definite integral and this one is our indefinite integral. So definite integral has these values from a to b. So we'd go ahead and put in our function, but I already typed in my function up here, so I'm just going to copy and paste it. And I want to integrate this with respect to x from a to b, and we have 0 to 3 here. And I get 177 over 2, so this matches perfectly. Let's go ahead and look at another example where we're integrating and trying to figure out whether it's true area or signed area. So for this example, we're looking at the integral from negative pi to 3 pi over 2 of the cosine of x dx. Okay, so the derivative of sine is cosine, therefore the integral of cosine is sine. So this is sine of x evaluated from x equal negative pi to x equal 3 pi over 2. We do our upper minus our lower, so I have the sine of 3 pi over 2 as my upper, minus the sine of our lower, which is negative pi. The sine of 3 pi over 2 is 0. The sine of 3 pi over 2 is negative 1. Kind of skipped ahead there. Minus the sine of negative pi is 0. So I get negative 1 for my answer here. Now negative 1 is the solution, but the question is this signed area or actual area? Well, the cosine graph we can look at quickly. The cosine curve looks something like this in either direction. And the points that I cross here at pi over 2, minimize at pi, 3 pi over 2, and then as I go to negative pi over 2, and then this point is a negative pi. So the area that I'm actually computing here is signed area, because here I have area below, here I have area above, and then here from pi over 2 to 3 pi over 2 I have area below. So again, remember, each one of these is an area. This is area of positive 1, negative 1, negative 1, negative 1, so you can tell that this sums to negative 1. So that's not true area, it's signed area. In the last example that we're going to look at, we're going to do some problems similar in the suggested homework set, where we're given generic functions and then we're asked to figure out what's going on with some integrals combining those. So we're given the function of f of x dx from 0 to 5 is equal to positive 5. And we're given the integral of g of x dx from 0 to 5 is equal to 12. And then we're asked to find out some particular information when we're working with these functions and combining them. The first example was we're going to change our limits of integration from 5 to 0 of f of x dx. Well, if you recall our rules, what ends up happening is this solution is just negated when you change your limits of integration from 0 to 5 to 0. So my solution here is just a negative 5. We could also look at the integral from 0 to 5 of f of x plus g of x. Well, I could split up each of these and look at the integral from 0 to 5 of f of x dx plus the integral from 0 to 5 of g of x dx. And I can see the first one is equal to 5, the second one is equal to 12, so combined they're equal to 17. And those are just using those characteristics or those properties of definite integrals, and this one definitely makes some common sense. We could also involve constants, so I could look at the integral from 0 to 5 of 2 of f of x minus 4 times g of x dx. So this would be 2 times the integral of f of x dx from 0 to 5 minus 4 times the integral from 0 to 5 of g of x dx. And of course I have my given up here. The integral from 0 to 5 of f of x dx is equal to 5. The integral from 0 to 5 of g of x dx is equal to 12. So I have 10 minus 48 is a negative 38. So that's what that value would simplify to. And again, I'm not sure if this is signed area or not because I don't know what these functions look like. I don't know if they're above or below the x-axis. But down here, when I get to this point, I'm thinking, you know what? A vast majority of this area is below the x-axis. So, section 5.2, Riemann sums. Toward the beginning, we were working with formulas, and we moved into definite integrals. And in section 5.3 and 5.4, when we're working with the fundamental theorem of calculus, this will also be reviewing as well. Thank you.